It is around 6:35, so we will go ahead and get started for this month. Welcome, everyone. I think there's a couple of new names in the list that I have or at least names that I haven't seen quite frequently. So welcome since I think most of you are actually joining us for the first time, which is always nice. This is the Astronomy Fundamentals Special Interest Group's monthly meeting. We normally have, when we have the presenters, the format of this meeting typically has two parts. We have a constellation of the month and a main topic. Unfortunately, we didn't have enough any volunteers this month for a constellation. So tonight we only just have a main topic for discussion, and it is on how stars are classified and organized by both professional and amateur astronomers. So I hope you will enjoy. So to kind of start off right in it, come on. What the? That's out of order. Sorry. Okay. So before we can start, we have to kind of talk about where where star classification actually has its roots in, and it starts with a Catholic priest called. Oh, sorry. Before I even go farther, can everyone see my? Has anyone issues seeing my screen? Before I always forget to ask that question and realize.
No problem. Looks good.
Okay. So we start with Angelo Ceici, who was a Catholic priest in Italy who served as the director of the Pontifical Gregorian Observatory in Italy. And he, this is mid 1850s, mid 1860s, so some of, obviously well past Newton with his first forays into using prisms to split light, which is one of the key tools. I'm losing my words here because but Angelo Ceici was one of the first scientists to what was among one of the first group of scientists to start pushing the idea that the sun was a star like every other star in the night sky. He was one of the first scientists to actually use spectroscopy to help study the night sky, and he has several inventions to his name, which for brevity I have not included here, which he used in his research to help investigate the color and patterns of stars. Spectra we view spectra by taking light of any color and shining it through a prism, and the prism will split the light out into its individual colors, which we then analyze for various means. But using the tools and techniques that he helped pioneer, he discovered that through his logs and observations that the stars he was observing came in several distinct types and subtypes. And with this collection of observations, he created the first star classification system, which bears his name and is called the Ceici classes, or Ceici classes. I hope I'm getting that right. Which he published in 1863, which during the middle of the American Civil War. So before we can get farther, we have to talk about exactly what spectroscopy is. It is one of the main tools used by astronomers and physicists and many other fields to determine the chemical composition of items. Of very they could be chemicals, trace element, many things. The way the use works, as I mentioned, is you shine light on or through something, or you excite an object by heating it, or bathing it in lasers, And this will cause the object to emit light, to re-emit or absorb light at specific frequencies, which will be unique to the chemical elements that make it up. For most astronomers, most astronomers, excuse me, will take light that they are collecting through their telescopes, and they will pass those through a prism or a beam splitter, if you're depending on how much money you have to throw at your instruments, and shine that onto a detector in order to capture the individual colors. Again, so not much difference there. The two main ways that we detect and analyze these colors are using absorption lines and emission lines. So absorption lines are the light that are seen as the absence of light that has been absorbed by a chemical body. And by that, I mean, if I take light and I shine it at a chunk of iron, the iron will absorb very specific colors of light and will re-emit and reflect back everything, every other color that was shined at it, except for those that it absorbs. And you can use that to analyze as one form of analysis and say, hey, this is iron, because we see that these specific color frequencies are missing. The reverse of that is using emission lines, which is what we are commonly used to analyze stars, where you look at the light that is being emitted by the object and doing splits on that. So it's kind of a difference. In one is you're looking for what is the absence of light from this thing I'm looking at. The other is looking for the presence of light, or how strong certain color frequencies are. So you might have a very intense red in some frequencies, and very weak yellow in others. So the CET classes were split out into 4 categories initially. There was a 5th category that was added much later by Secchi himself. But they were basically split into the constituent colors. White and blue stars were class 1, yellow stars fell in the 2nd class, orange and red into the 3rd, and then carbon stars, which he which he actually discovered on his own, were split into a 4th category. Looking at not only the color, but he also used the intensity of hydrogen, how bright hydrogen frequencies are in the stars to help aid his classifications. So before CHE could help do this, they had to actually determine what were the colors of light that were emitted by hydrogen. And this was done by a few other prior scientists who, unfortunately, I cannot recall their names off the top of my head. The right in this picture that is kind of blurry, unfortunately, I apologize for the poor quality. I thought that would look better, are examples of the spectra matching 4 of the 4 Secchi classes, with the top being class 1, the bottom being class 2, and the middle 2 being class 3 and class 4, respectively. So it's kind of inverse. So you can see how these are all emission lines showing. So the presence of colors here is showing where helping us determine like what actually is in the star. And the stronger the specific color is the strength of that particular element. They use a way to say how abundant that specific element is. So
excuse me, Connor.
Hey, Doug.
Those spectra are actually showing absorption lines.
Thank you for correcting me.
And I believe the hydrogen series was named after, I think it's called the Balmer series.
I'm not quite sure what you're referring to.
The hydrogen series of lines that you were talking about, he's using here too. I think it's the Balmer series.
I will have to trust you on that. That it does not ring a bell from when I was looking at this. but I was also
Okay.
kind of rushed to put this presentation
Okay.
together because of a lot of other stuff. So you may very well be right. I don't have enough information to respond to it though, so I apologize. From the Secchi system, we move on into the Draper system, which was created by Edward Pickering at Harvard Observatory with the help of the Fleming computers. Sorry, excuse me, that's not the correct word. With the Harvard computers, they were mostly women who Pickering had hired to help him in his work, because the graduate students felt that the work that these women were doing was beneath their talents. And the group of women that Pickering employed went on to become very notable astronomers in their own right. And there was Doug Smith put on a presentation in October that details a lot of the achievements that were made by the women that Pickering hired in more detail. But we'll focus to the Draper system was primarily assembled through the efforts of Wilhelmina Fleming, who worked through, I think it was around 10,000 photographic plates, and using a small little eyeglass was looking at the spectral lines that were burned into the plate by the prisms they were using to do spectroscopy. That was how they did this back before we had modern digital computers, is they would take the prism and then split that light and then shine both the star field and the spectral lines that they were looking at onto the photographic plate. And then they would look at those with a magnifying glass later to help figure out what the stars were. It's very, very time consuming work to sift through that many photographic plates and spectra, and Wilhelmina Fleming assembled almost 10,000 observations of this type. Following the Secchi classes, her work further split them into subclasses denoted by the letters A through P for primary star spectra, and she added in Q much later for non-stellar spectra, which included things like planetary nebulas. The letters were used to denote how strong the emission line, a hydrogen emission line, basically how intense or how much hydrogen was in that object, with A being with stars of class A of the subtype A having the strongest hydrogen emission lines, and P having the weakest hydrogen emission lines. It was the Draper catalog and the Draper system that were later used to assemble what we now know as the Hertzsprung-Russell diagram, which I have some pictures of here later, and it is a phenomenal tool for helping explain many things about stars. And so to kind of summarize here, so we have the Seiichi classes in the left-hand column, the Draper classes in the center column, and then kind of just showing how these were all lined up. So, and where the two systems overlapped with each other. So the Draper system was an extension of the Secchi system, so that you would catalog a star as type 1A for being for different types of stars, and so on. The Harvard system, which was the next iteration in our star classification, was made by Annie Jump Cannon, who was a part of the Harvard Computer Girls. I'm getting their name horribly wrong, but she was one of several women that was working with Wilhelmina Fleming at the time. And I have an incomplete item, I apologize. But she was also using photographic plates as well in her research. She took the Draper system that Fleming had made and dropped all letters except O, B, A, F, G, K, M, and N, which getting us closer to the modern classification system that gets used today. She also kept P around, which was used for planetary nebulas, but this has been dropped from our modern classification systems, as well as N. So in addition to that, she added numbers to serve as a scale to show transition points and where a star fits between two different classes. So for example, if someone said a star was an F2G, this denoted that the star was in the F class and about 1/5 of the way to the G of being on the line between F and G. These two are both are collectively known as the Hertzsprung-Russell diagrams, which I mentioned a few slides ago. They show how stars, the relationship between a star's color, its luminosity, or how much light it emits, and its temperature. It's kind of hard to read here. So the temperature scale is up here at the top. The luminosity or brightness is over here on the left, and then the color is down here on the bottom, with red being farther right and white being farthest left. And if you took all the stars that were cataloged by Fleming and Draper and you plot them into this graph, you plot them, their relationship, you get this. And it shows the stars and how they change over time. Main sequence stars and subgiants and supergiants. The main sequence stars, supergiants, and hypergiants, which are over here on the right. I'll talk a little bit more briefly about those later in the presentation. I didn't have time to go into giants and subgiants. And we'll also go around, talk about these letterings here in the coming seconds. But this is one of the most significant works that came out and helped basically quantify, helps guide us on determining what the evolution of a star is. The modern system today continues with the Harvard system from Annie Jump Cannon and augments a few things with it. It adds in some the Roman numerals to help determine it adds in some additional numbering onto the letter classes O, B, A, F, G, K, M, and N to help communicate at a glance not only what the star's color is, but also its temperature and its specific subtype. So you can look at a glance and know if a star is a hypergiant, giant, and so on. Which is what we see back up here. We have the O Roman numerals 1, 2, and 3, 4, and 5 to denote O being hypergiants, 1 being supergiants, and 5 being for dwarfs and main sequence stars. Oh no, back here earlier. So again, slightly in a more tabular form. You have hypergiants, supergiants, main sequence stars, and subdwarfs, all denoted by a specific letter. I'll have some better examples here in a second. So O-class stars are the hottest and most luminous main sequence stars. Most of these next slides, I'm referring specifically to main sequence stars because there's a lot more than compared to some of the other types like supergiants and giants. O-class main sequence stars are the hottest and most luminous main sequence stars in the night sky, and they emit almost all their light in the ultraviolet range. So even though there are several O-class stars very close to us, like within the Orion Nebula, because all their energy is coming out of the ultraviolet range, they're not nearly as bright as to our eyes or through normal optical instruments compared to other stars, such as main sequence stars like or supergiants, giants, and hypergiants. These stars bluish white in color to the naked eye or to instruments, and they have a surface temperature ranging from around 25,000 to 50,000 Celsius, which is ridiculously hot. They are among the rarest type of star, main sequence star in the night sky, with about 1 in 3 million stars actually being in the O class. These stars are around 40,000 to 1 million times more luminous than the sun. They have very short lifetimes. They typically live for about at most 10 million years before they explode, typically as supernovas, and may eventually turn in, and some of them even turning into black holes. The mass range of these stars typically falls between 15 to 90 times that of our sun. Moving down the chart, we wind up at B-class stars, which these are a little bit more towards the blue end of the spectrum. They're significantly cooler than O-class stars. They are separated in their spectra from O-class stars by the presence of neutral helium emission lines. Excuse me. So to differentiate their neutral helium, when astronomers talk about light, there's typically a couple of different ways that they do it, primarily being ionized or neutral. Ionized spectra means that there's enough energy that the atomic nuclei, in this case helium, doesn't have any electrons around it. And so this changes the emission spectra of that element slightly compared to the neutral form, where the electrons are still in orbit around the atomic nucleus. B-class stars have a temperature range from about 10 to 30,000 Celsius, so significantly cooler, still really, really hot. I would not want to stick my hand in either of these stars. And they're a little bit more, significantly more common than O-class stars, with instead of being 1 in 3 million to around 1 in 800. As we get farther and farther down into the cooler stars, that they become significantly more common. B-class stars are typically in the mass range of about 2 to 16 solar masses. They have a lifetime of about 100 million years. These stars can end as both supernovas or as white dwarf stars. From there, we have the A-class stars, which include our friend Sirius, who is coming up here in the night sky. These stars are kind of similar in color to B and O-class stars. They occupy this whitish blue part of the color spectrum. The main differentiator between an A-class star and a B-class star is because these stars are a little bit more cooler and they have an extended lifetime, is you start getting the presence of other metals in the stars spectrum, such as carbon, titanium, and a couple of others. These stars also have a significantly stronger hydrogen emission line compared to the other stars around it. The A-class stars have the strongest hydrogen emission lines of all of these stars in the Harvard system. And about 1 in 160 stars, main sequence stars, will fall into the A-class range. These stars are fairly close to the sun in solar mass, with about 1.5 to 2.1 solar masses. Although they are not nearly as long-lived as the sun, they still are quite up there within the 1 billion years time frame. Excuse me 1 second. kind of a little intermission here, showcasing how the star classes change as they get cooler and cooler. So on the right, O class stars are, as you get higher and higher masses, these stars are significantly bigger and brighter. O classes being the largest, B and A, and you start getting smaller and smaller stars from there as the stars get into cooler ranges. So on the next stop after F and after A class stars are F class stars, we're still moving into cooler stars here. They have a temperature of around 6,000 to 7,000 degrees Celsius. What separates them apart is that they are a whitish, start getting into the whitish yellow portion of the color spectrum. They are separated out from the categories beneath, such as the G and M and K classes, by the strong presence of calcium-2 in their emission lines. But they also include trace amounts of other metals, trace amounts of ionized metals as well within their spectra. These stars are slightly larger than the sun, typically between 1 to 1.4 solar masses, and have an average lifetime of around 5 billion years. From there, we move on to G-class stars, which is the star class that that the sun is a member of. Its spectra includes various metals including both neutral versions and ionized versions within the spectrum. They have a mass range of about 0.9 to 1.1 solar masses. So our sun is almost smack middle of the mass range of the G-class variants. About 1 in 13 stars are G-class stars. They typically have a white yellow to whitish yellow color, and surface temperatures of around 5,300 to 6,000 Celsius, with an average lifetime of around 10 billion years. From there, we almost through with the classes of star. With this list, we have K-class stars, which include Arcturus and Aldebaran. Both of those stars actually aren't main sequence stars, but to give you an idea of a star in the night sky that you might want to look at, say, hey, does this fit? Arcturus and Aldebaran are in this class. The main spectral characteristic to finding K stars is that they have a very high presence of heavy metals such as iron and calcium in their spectra. They are getting into stars that are less massive than the sun by a fair amount. They overlap some with the lightest with M-class stars in their mass ranges. They have a mass range of about 0.5 to 0.8 solar masses for K-class versus about 0.5 to 0.6 for the M-class stars, which we'll talk about here in a second. And they have a surface temperature of around 3,900 to 5,000 Celsius. And they are strongly orange in their color. They are, because they are much lighter than the sun, their luminosity is typically about 1/2 that of the sun. And about 1 in 7 stars are K-class stars, and they have an expected lifetime of about 50 billion years. And finally, wrapping up on the list of star classes, we have M-class stars, which include Betelgeuse and Antares. Again, neither of those stars are actually main sequence stars, but in terms of finding things that you might want to go look at. The main thing that differentiates M-class stars from the nearby K-class stars is that these stars have high large amounts of titanium within their spectra, and these are the most common type of stars in the universe. 3 out of every 4 stars are M-class stars, but because they are have such small masses compared to all other stars, they are also not very luminous. The brightest M-class star that can be seen from Earth has a visual magnitude of about 6.7. So anytime you're in the night sky, any star you look at without a telescope is most certainly will not be an M-class star. You can only see M-class stars through a telescope. You cannot see them with the unaided eye. They're just too faint. These stars are the longest lived of all stars. In fact, we actually don't know how long they can live. We can only model them. Excuse me 1 second. So Luke, your question is, why aren't these stars alphabetical? I wasn't actually, that was a question I myself was really curious and trying to answer as well with this presentation, but there isn't really a strong reason why. The main reason that the O and A are flipped has to do with the switch over between the Secchi classes and the Draper system, but that was really more without getting really deep into the science behind why that decision was made. It's hard to really answer, but why specifically when Annie Cannon was publishing these classes with the Harvard system, it's not really explained well. I would probably have to go back and look at her actual paper that was published with the Harvard system in order to answer that question, and I simply didn't have time to do that. No, it is one of those things where you're just like, why couldn't they just have everything in alphabetical order? And the answer really was, it was at one point, but then people started moving things around because of other characteristics, and then you wound up with O being the first in the list. That is an excellent question. Continuing, where was I? Right. So M-class stars, these are the most longest lived stars in the universe. We actually can only estimate their potential ages, maximum age, because the universe hasn't been around long enough to see any of these stars die. They have estimated lifetimes with 100 billion to 1 trillion years, and we could only model in computers how long these stars would live. Okay, where did my mouse? There it goes. So kind of recapping what we've gone over so far, we've covered most from all the way here from M all the way to O in terms of stellar classes, and we're talking a little bit about here. Finishing up here with a brief talk about hypergiants and supergiants. I unfortunately ran out of time to include some information here on bright giants, giants, subgiants. The articles I was wanting to include were a little bit heavy on the science, and I didn't have time to actually break it down into something that was more digestible for this. So we'll only touch on some of the 2 subgiants, which are usually the ones people are most excited about because they think, ooh, it's really big. So the first on the list as I move here to the end of this presentation are supergiants. These stars are the largest and most luminous stars. Earlier I had mentioned that O class are also very large and very luminous. That was applying to the main sequence stars, and supergiants are a significantly larger and a significantly more luminous than even the largest O class main sequence stars. These stars would have a diameter typically within the range or magnitude of 700 to 1,000 times the diameter of the sun. So if you took a supergiant and you kicked the sun out of our solar system and put a supergiant in its place, Jupiter would be inside the supergiant. These supergiants are typically donated by the luminosity class 1A and the class 1B. So you would see, so example, a supergiant might be cataloged as an A5 1B to denote, this is a class A. It has a temperature, a middle range temperature for an A class star, and the 1A and the 1B noting that the star is a supergiant. Okay, well, let me get through these last two slides, Doug, and then you can answer the question we had earlier about why things aren't, why astronomers can't use things in alphabetical order. So supergiants are typically the next phase that a star will transition to once it leaves after the main sequence. Main sequence stars are where stars will spend most of their life. And then once these stars have exhausted the hydrogen in their cores, they transition into some other type of star. Supergiants are one of the transition points. These stars are formed by when the star, as I mentioned, the stars exhaust the hydrogen in their cores. They begin to fuse helium, which triggers a massive expansion of the star and triggers to their tremendous size. Once these stars exhaust all of their helium fuel, they will then typically transition into a white dwarf star, which will also be similar to this. Our sun will not, although our sun is not massive enough to be a supergiant, it will actually transition into a normal red giant, but then will also end up as a white dwarf. And then at the tail end of here, we have hypergiants, which are kind of this black swan of the star classification. They're not really well defined. There's kind of a lot of arguing about whether or not hypergiant should even be a class at all, or a subtype of star at all. The main characteristic that separates hypergiants apart from supergiants is when you analyze these stars, they are losing a lot of they are very unstable, and so the fusion reactions in the star and a couple of other characteristics mean that the star is actually blasting a lot of its own mass off as it continues to undergo nuclear fusion. And that this mass loss and instability are the only thing that really separates them out from hypergiants from supergiants. But of particular note with hypergiants are yellow hypergiants, which are denoted as class G, like as class G0 and G1A. Of all the stars, and main sequence included, these are the rarest type of star, with just 15 of the yellow hypergiants known in our entire galaxy. So we go from 1 in 3 million from a typical main sequence O class star to 15 in 400 billion. These stars are thought to be kind of a transition point between O class stars, O class main sequence stars, and red supergiants. We think that stars only spend about a few thousand years as a yellow hypergiant before they transition into a red supergiant, which is the main contributor for their rarity. If only spend a few thousand years, is a metaphorical blink to most of us. So, of the yellow hypergiants we know of, most of them are only as old as about as young as human civilization since the Egyptians. They They do not spend a lot of time in this period at all before they go into red supergiants. And that's kind of it for this talk that I had. I know some of it was a little bit scattered, and I do apologize for that. I wanted to have this a little bit more well put together, but I was running out of time because I had to deal with some stuff for school and for work. And so this may have been a little bit more scatterbrained than what I would have liked. And for that, I do apologize. Doug, you said you have an answer to our question.
Yeah, I looked it up. You have to know the right place to look. So as it turns out, the original classification scheme that was proposed before the Draper finalized their "Oh, be a fine girl, kiss me" thing, before that, there was a classification scheme that they were using at Harvard Observatory based strictly on the amount of hydrogen in the star. Not the amount.
That would be the Draper system.
No, before that, there was the hydrogen intensity of the lines, and that was alphabetical. The A, B, C. There was actually 22 categories in that original classification scheme, based on hydrogen intensity of the spectral lines, and that was felt to be too clumsy and not very useful, basically. And they decided, instead of using hydrogen intensity in the spectral lines, they switched to using the classification based on temperature, which is what it is today. It's based on temperature. And that's how come the classifications, and they dropped a lot of them. And so that's how come you went from 22 down to, what is it, 7 or 8. And also the order got scattered.
Yeah.
Because of that.
So the Draper system is the one that started out with the A through P, and then between the Draper system and the Harvard system is when they did that swatch.
So that's where it came from.
So that was kind of it. And with that, I'm going to go ahead and end this recording. And that was all kind of we have on the agenda for tonight. Does anyone have any questions about, actually before I end this recording, does anyone actually have any other questions about the presentation that, I might hopefully be able to answer?
This is Matt. Hello. I was just curious, like what's the range of like the classifications that you guys can see, like when you're just out looking in like your backyard? Do you see like the really big ones, like down to
everything?
You could, so most stars that you can see, even with your unaided eye or with a telescope, you typically won't see a significant color like you would be expecting if you were to safely look at the sun. Keyword safely. Please don't look at the sun without protection. Even the sun is still mostly a white because of how much light it gives off. You need a little bit more work to see the predominant yellow in the sun. So most of the stars, when you look at them, will be white points of light, but with some exceptions, such as carbon stars or Betelgeuse and some of the more redder giants and supergiants, you can see them as some shades of red, but most of them with your eyes you will just see them as various shades of white.
But Matt, there are examples of every type of star in the classification system that you can see naked eye.
Yeah. So since I did include those, so for example, all of these star names here. So in Mintaka is an example of an O-class star. This is a star, I think that's in Orion's belt.
Yeah.
I think it's the center star.
I don't know.
Of the belt.
And, there's Vega and Sirius are your A stars and so on.
Yeah.
Rigel star can be seen.
Rigel and Regulus are examples of B-class stars. A lot of these stars in this catalog are actually in Orion. So Orion, which is coming up which is actually up now, is a really good spot to do a tour of like what are all the star classes that I can see. Vega, Deneb, and Sirius are examples of some A-class stars. Sirius, you know, is coming up here right along with Orion, so you can actually see that one. Canopus and Procyon, again, also in the direction of Orion, but in the constellation Canis Major, an example of an F-class star. G-class stars include the Sun, so you know you can see one of those pretty much every day of the year. If you can't see one every day of the year, then something has gone horribly wrong, and we're all about to die.
Are you able to see like red dwarfs and stuff? Can you just like if you have a telescope?
There are some.
You can't. No, there are no red dwarfs you can see naked eye.
I think there is.
No, the brightest red dwarf star you can see with your eye is magnitude 6.7, which is beyond human vision.
I was just curious if like even if you have a so I don't have a telescope or anything yet, but like when you're even if you had like a really crazy telescope if we're looking at it, like would you see, would it be red to your eye, or does it not show in that wavelength?
I am not quite sure. Matt, I will, given that these are that M-class dwarfs specifically are not very luminous at all. My best guess is you wouldn't see much of a color. But I do know that there are some stars like Bernard star, for example, which I think is an M-class star, which you do notice a very distinct red to.
So I have looked at some M-class stars through an 8-inch telescope, and you do see some reddening, a little bit of the color.
Okay.
And to finish up for a K-class stars, Aldebaran in Taurus is an example of a K-class star that you can go out and look at tonight. But for most M-class red dwarfs, you do need a telescope or binoculars to be able to see any of them. You will not see them unaided eye. So excellent questions, Matt. Cool. Any other ones before we call it a night? Awesome.